In this lecture, we illustrate the bisection method for approximating the solution to the equation f of x equals 0. For this example, f of x equals minus x squared plus e to the x power. We are going to use a spreadsheet to get an estimate via the bisection method that is strictly within 1/1000th of the exact solution. The bisection method requires two conditions to guarantee its success. First, there has to be two different x values where one y value is negative and the other y value is positive. In our example for f of x, f of minus 1 is minus 0.6 up to 1 decimal place, while f of 0 is 1. The viewer can certainly use a shorter interval that contains the solution and whose endpoints are much closer to the exact solution. This can result in fewer iterations for the bisection method. The second condition is that f must be continuous on the closed interval with these two x values as the endpoints. F of x is minus x squared plus e to the x power, so that f is continuous everywhere on the real line. On an added note, as an exercise for the viewer, one can prove by using f prime of x that f is a strictly increasing function on the real line, so that f of x equals 0 has exactly one solution. We will use the GeoGebra spreadsheet, but we imagine that most spreadsheets can handle the bisection method. However, we have had problems using Microsoft Excel when calculating minus x squared. The viewers can try this out with Microsoft Excel and see what kind of result they would get. We will use 6 different columns for this exercise. On the first row, we label what goes into each column. The first and second columns will have the left and right endpoints respectively of the interval at each iteration. A sub n for the first column, b sub n for the second column. The third column is for the midpoint c sub n of each interval. The last 3 columns will have the y values of the entries in the first 3 columns respectively. F of a sub n for the fourth column, f of b sub n for the fifth, and f of c sub n for the sixth column. The first left endpoint, which is a sub 1, is minus 1, and the first right endpoint, which is b sub 1, is 0. The midpoint c sub 1 involves a formula, and for this we start the entry in cell G2, where c1 goes, with an equal sign followed by half or 0.5, times the sum of a sub 1 and b sub 1. A sub 1 is in cell E2, and b sub 1 is in cell F2. The midpoint minus 0.5 is the first midpoint estimate for the solution R. F of a sub 1 also involves a formula, so we start the entry in cell H2 with an equal sign followed by minus a sub 1 squared. A sub 1 is in cell E2, so we have minus E2 squared, plus E with exponent a sub 1. And so we have e with exponent e2. Now that we have f of a sub 1, we can generate f of b sub 1 and f of c sub 1 by simply dragging the handle of f of a sub 1 all the way to cover f of c sub 1 or cell J2. For the new left endpoint a sub 2, which goes into cell E3, we start with an equal sign followed by an if-then-else statement. If the product of f of a sub 1 and f of c sub 1 that are in cells H2 and J2 respectively is less than or equal to 0, then the new left endpoint is still a sub 1, which is in E2. Otherwise, the new left endpoint is c sub 1, which is in G2. For the new right endpoint, which goes into cell F3, we again start with an equal sign, followed by an if-then-else statement. The inequality is again f of a sub 1 times f of c sub 1 is less than or equal to 0, or h2 times j2 is less than or equal to 0. Then the new right endpoint is c sub 1, which is in G2. Otherwise, b sub 1, which is in cell F2, is the new right endpoint. For the midpoint of this new interval, we drag the handle of C sub 1 or cell G2 to cover cell G3. Then we calculate the y values for the second iteration entries by dragging the handle of the y values from the first iteration. We now propagate the formulas of the second iteration to an appropriate number of rows to get an estimate that is within 1/1000th of the exact solution x equals r. To determine how many rows we need to do this, we first note that we are cutting each interval in half at each iteration. Our starting interval, whose endpoints are -1 and 0, had length 1. So the absolute error of our estimate, which is the absolute value of r minus c sub n, is less than or equal to 1 divided by 2 raised to the nth power. Now, 1 divided by 2 to the 10th power is equal to 1 divided by 1024, and this is less than 1/1000th. And so at iteration 10, we will have obtained a midpoint that is strictly within 1/1000th of the exact solution. So we drag the handle of row 3 to cover all the way down to row 11 for 10 iterations. The exact solution x equals r is now between these two endpoints. C sub 10, which up to 4 significant digits is -0.7041, is the first midpoint estimate that is strictly within 1/1000th of the exact solution. As a final note to this example, an error bound for the midpoint estimate C sub n at the nth iteration is given by the absolute value of b sub 1 minus a sub 1 divided by 2 raised to the nth power.